So those are the inverses. We just verified that f and g are inverses. I had to stop the video and start a new one. I think there's a 15-minute time limit, so this is part 2, just continuing on here. So I'm going to look at how do we find the inverses if I just give you a function and I ask you to find the inverse algebraically, which is the method you're going to want to use. So let's begin with defining a function, and we're going to find the inverse of, and we'll just start with f of x equals 1/3 x plus 4. We know that's a function. If we were to graph it, it would be a straight line. It passes vertical line test, so we are talking about a function. So let's see what we do. Earlier on, I told you that the inverse of a function has the property that the function and the inverse switch domain and range. So we're going to take advantage of that. I'm going to think of this function, instead of f of x equals 1/3 x plus 4, I'm going to think of it as y equals 1/3 x plus 4. First thing I'm going to do is I'm going to switch x and y. Then I'm going to solve for y. So what that'll look like is I'm going to literally take where y appears, I'm going to call it x. And this said x, so I'm going to replace that with y. If I solve this for y correctly, then I should have the inverse of that function. So I'm going to have x minus 4. I'm going to subtract the 4 over to the left side. And what I have to do then is take both sides times 3. Well, that's going to look like this. And we distribute and get 3x minus 12. And I'm going to call that the inverse. So f inverse of x is 3x minus 12. Now, if what I told you previously is true, then we should be able to verify this. So I'll run through that example with you. Once again, I want to show that f of the inverse gives me x, and I want to show that f inverse of f of x is also x. That's what I want to demonstrate. And that will be verifying that what I did is correct. So I am saying this is my inverse. Okay? Well, let's look at the first one, f of f inverse of x. What that means is I'm going to take f of 3x minus 12. So 3x minus 12 is going to replace x in the f function. Okay, so that's going to replace this here. So I'm going to have 1/3 parentheses x minus 12. Okay, that's like the 1/3 x. And I still have plus 4 at the end there. So I have plus 4 at the end here. I'll distribute. 1/3 times 3 is just 1. 1/3 times 12 is 4. And I have plus 4. You can see that minus 4 and plus 4 cancel. And it looks good so far. So let's verify f inverse of f of x. This means f inverse of, what was f of x again? We got to look up here. 1/3 x plus 4. So this 1/3 x plus 4 is going to replace x in this guy. So it's going to go right there. So 3 times that stuff minus 12 is what I got to do. 3 times 1/3 x plus 4 minus 12. I took 1/3 x plus 4 and I put it in for x into the function inverse. If I simplify, I should get x, and that will have verified that I do have the right inverse. So I distribute here, I get x plus 12, and then I get the minus 12 at the end, plus 12 and minus 12 cancel, I get x. So I've definitely got the inverse here. So to put it in one spot, I have the function f of x, which was 1/3 x plus 4. And I got the other function, f inverse, its inverse, which is 3x minus 12. There it is right there. There it is, 3x minus 12. I want to talk about the graphs of those two functions. They both are functions. Now, a function and its inverse, the graphs should be symmetric across the line y equals x. So I want to demonstrate that with a graph here. So let's see if I have enough room to extend a couple more times. Let's bring up a graph. Let's get this out of the way. There's the content. All right, so here is a graph. Bigger. The first one, 1/3 x plus 4, the function f. I know that the y-intercept is 4, and the slope is up 1/3, 1/3, or down 1, left 3. Now that's our line. Let's see if we can get this pretty accurate here. There we go. Okay, that's our arrow over there too. That is our function f of x. Now I'll put the line y equals x. I will put that as a dotted line up here. Okay, y equals x is going to go through 10, 10, 9, 9, 8, 8, 7, 7, and so on. All the points that have the same x value as they do the y value. So now when we plot the other line, the inverse, which is 3x minus 12, well, unfortunately, minus 12 is down here, about there. Okay, we'll get an accurate graph here. We'll look at the table. Where it's going to go from there is up 3. So if I went up 1, it would be 11, 10, 9 over 1. So my graph is going to go through here. Okay, you can verify that by plugging in the number 1, which would give me 3 times 1 is 3, minus 12 is negative 9, so I'm in the right location. And I can just go up 3 over 1 a couple more times, and that's where this line is going to go. So I'll graph that. I want this to be a solid line. We can change that. Okay, so something about like that. You can see that those two graphs are symmetric with respect to the line y equals x. The line y equals x serves as a line of symmetry for these two graphs. Anytime you have two functions that are inverses of one another, this will be true. What you have to watch out for, though, is sometimes the inverse of a graph may get flipped. Let me reduce this here. Let's move this. Where we run into a problem, though, is sometimes if I graph the original function, it may look something like this, like a parabola, poorly drawn, but nonetheless a parabola. Here's my line y equals x, something like that. Imagine that goes right through 0, 0. Well, the inverse of that is going to be something over here like this. And we can see that this is not a function because it fails the vertical line test. The vertical line touches at two places along the same vertical line. So in those instances, we have to be cautious and be aware that both the function and the inverse are supposed to be functions, which this would not work here. This we would say that this function, even though this is a function, it does not have an inverse. So it's not true. I can't just give you any function and expect there to be an inverse all the time. Sometimes there is, and sometimes there isn't. So how we address that problem, or how the mathematicians addressed it, is they introduced the concept of a function being one-to-one. So right here we will define what a one-to-one function is. A one-to-one function. A function is one-to-one if for any value a and b in its domain, that if the function at value of a is equal to the function value at b, the only way that's possible is if a and b are the same exact number. Now that's not true with a parabola. Okay, if I look at a parabola, let's do a quick sketch here of one. If I look at this parabola right here, this is not one-to-one. Because, for instance, let's say this particular y value of, let's just say this is 4. Let's assume that this is the graph y equals x squared. It's not one-to-one because there are two different x values that both give me 4, -2 and +2. That's not one-to-one. Here we have two function values. I have the function value of -2 is equal to the function value at +2. And you can see that these are different values. So this is not one-to-one. And therefore, it does not have an inverse. So the only way that a function is going to have an inverse is if that function is one-to-one. The nice thing is, we can tell by looking at a graph very easily if a function is one-to-one, because we have something called the horizontal line test. Basically, for a function to be one-to-one, a horizontal line cannot touch the graph in more than one place at any given point. Here we see that this horizontal line touches the graph at more than one point. This tells us that this graph is not one-to-one. Okay, even though that's a function, it is not one-to-one, and it therefore does not have an inverse. What I'll end with here is a quick demonstration of how to test algebraically whether a function is one-to-one. So I'm going to borrow the problem out of our text here. Let's suppose that the function f is equal to the square root of x plus 1. Now remember, if it's one-to-one, that means that if the function values are equal at two different points, okay, what that tells us is that if it's one-to-one, a and b have to be the same value. So if it's possible for me to get the same value with two different x values, then this would not be one-to-one. So what we're going to do is we're going to say, all right, let's replace x with, let's call it a for f of a. Okay, function value at a would be square root of a plus 1. Function value at b would be the square root of b plus 1. I'm going to set these two things equal to each other. I'm going to say, well, what would it take for the square root of a plus 1 to equal the square root of b plus 1? We look at this and we'll notice that the 1's cancel, and I'm left with the square root of a is equal to the square root of b. Well, the only way that's possible is if a and b are the same value. So what we've just showed is that this function is one-to-one. And that therefore will have an inverse. All right, so what I want us to try here for this particular section, section 1.6, put this stuff to practice here on page 69. We're going to skip the vocab section at the top, but right beneath that line, we'll start with number 1, and we'll go 1 through 19 odd. I want to do 21 to 24 all.